In this video, we're going to apply hybrid theory to some molecules we've seen to talk about what is the hybridization of those molecules. So let's look at carbon dioxide. Well, if carbon wants to bond to oxygen, it needs an orbital that can reach out into space and do so. And at the moment, we won't talk about oxygen's orbital. We'll just draw it as a sphere here. But carbon needs to have an orbital that reaches out in both directions. It needs to reach out towards both oxygens. Those oxygens are 180 degrees apart. They're linear. They need to be on opposite sides. The only combination of hybrid orbitals that do that is sp. sp orbitals are 180 degrees apart. And so carbon has to hybridize two of its orbitals to deal with the fact that it has two things around it. And this is, you'll think back to our Vesper shape idea, carbon has two things. Therefore, carbon needs two hybrid orbitals. Now, carbon has four bonds. If we draw out the Lewis structure, carbon double bond oxygen, double bond oxygen. Only your first bond is ever a hybrid. So only first bond between atoms is hybrid. If you have a second or a third bond, that is not a hybrid orbital. We could try it. If you tried to do that, you'd have carbon, you'd have a hybrid orbital going this way, a hybrid orbital going that way. They'd be 109.5. You could try to have your oxygen do the same thing. Two lone pairs, hybrid orbital, and they'd overlap on top and bottom. This is a weak overlap. At 109 apart, these are held very wide. This does not put a lot of electron density in between the two. It puts it off to the sides. This is not effective at holding a molecule together. Instead, what happens is if your carbon has only one hybrid orbital, and your oxygen does the same thing, well, end on end, they overlap really well. You get those electrons in the middle, you get lots of overlap. And what happens is they still have p orbitals. And we draw p orbitals small, but the reality is they're actually wide. They are bulbous orbitals. Just hard to draw that on our drawings most of the time. They're diffuse, but they do overlap. And I didn't draw it the greatest here. They can overlap a little bit. Your first bond, by being directly towards the other atom, has a wonderful overlap. And the more overlap, the more your electrons are sharing, the stronger the attraction. Your second bond is weaker than your first. There's not as much overlap when your p orbitals overlap. But the sum of the really good and the weaker is still better than the two not great if you tried to use two hybrid orbitals. The net effect is you are more strongly bonded if you have this configuration with one hybrid and one set of p orbital interactions. Well, we have some terms for it. If you are end on end, so end on end, this is a sigma bond. Sigma bonds are much better at overlapping. So they are stronger as a general rule. You then have the option for your multiple bonds, if you have them. We kind of just draw them overlapping on top and bottom. Now remember, this is a p orbital. It's the whole shape, so it is overlapping simultaneously on top and bottom. They're not two different ones. This is one shape. But it has that top and bottom overlap. This is a pi bond. Pi bonds are weaker than sigma bonds for the same atoms, but they are where you get your second and third bond if you have them. They come from the unused p orbitals. So way back here we said, hey, to get that 180 degrees, I needed my oxygens to be on opposite sides, and only the sp orbital did that. That's because there's still 2 p orbitals left. So I had an s, I had my 3 p's, 2 of these went to hybrids, 2 p's were left. Carbon still has a p orbital going up and down. These oxygens, if we build their hybrids here, they still have p orbitals. They can reach across like this. The other oxygen here has its hybrid nicely overlapping. Well, this does raise an interesting idea. To make my hybrids go left and right, I used my left and right p orbital. So my left and right p orbital got used with my s. So they're gone. I just used my up and down p orbital. The only remaining p orbital is the in and out p orbital. That's actually the one that bonds to the second oxygen. They overlap this direction. That second oxygen can't overlap with the up and down p orbital on carbon because it's already been used. There's already electrons in it. It was used for the left oxygen. Those unhybridized p orbitals get used to make your second bond. And this really does work this way. If I have a carbon to 2 hydrogens and a carbon. And so let's do CH2, double bond carbon, double bond CH2. Well, that first carbon, it has 3 things. 2 hydrogens and another carbon. If it has 3 things, it needs 3 hybrid orbitals. So it needs sp2s, 1 s and 2 p's. It is a sp2 hybridized. sp2s were 3 things. All of them are atoms. This is trigonal planar. It's going to be 120 degrees. It has a hybrid orbital reaching out towards this hydrogen, overlaps the hydrogen's s. It has a hybrid orbital reaching out towards that hydrogen, and it has a hybrid orbital reaching out towards this carbon, which has its own hybrid orbital. And you could carry that on to your next carbon and its hydrogens. And you might at first be inclined to say, and I'll draw these ones in green, that it should look largely the same. Well, let's factor in those p orbitals. So we're going to put those hydrogens over here flat. And so draw this a little bit better. These are going away and coming towards us. These are very much flat, almost perfectly like looking on the side piece of paper. Right? Angled it just slightly, but imagine that you're looking at the edge of a piece of paper. To make the second bond to my middle carbon, well, which p orbitals did I use? For my sp2 here, I had to use the left and right one, and I had to use the in and out one if I wanted my hydrogens to be able to go in and out. So the only p orbital remaining is the up and down one. There's no up or down around that carbon at the moment, so its hybrid orbitals don't have any up and down direction. They didn't merge, they didn't hybridize the up and down p orbital. And so that is the remaining p orbital. This is the free one. Well, we said our center carbon was bonded to 2 things, or we can say that. It's bonded to 2 things. It goes to that carbon and that carbon. So this is a 2 thing, which means the center one is just sp hybridized. it has 2 remaining p orbitals that didn't get used. So which p orbital did get used? Well, it bonded left and right, so the left and right p orbital. So this one used its left and right already. The up and down is still free. And so it can overlap the up and down to the left carbon. Well, that means it's used up. When we want to double bond to our right carbon, I can't go up and down. I have to use the right carbons in and out. That's the only way we're going to get that second bond. And if we think about our right carbon, it's got 3 things around it. It's going to be sp2 hybridized. And so it only has 1 free p orbital. If I need it to be the in and out one that's free to form the double bond, that means the hybrids have to be the up and down and the left and right. Well, go back and look at my hydrogens here. We had drawn them kind of just like the other ones, but if the only ones for hybridization that are free are up and down, then they've got to go up and down. Which means those hybrid orbitals, the sp3s that we make, they look like they're flat in our face. Instead of on the edge of a piece of paper, this is looking straight down on a flat piece of paper. This carbon over on the right looks like it is trigonal planar, but you're looking straight down on it. And the carbon over on the left is trigonal planar, but you're looking at it edge on. The net effect is these hydrogens have to go up. And so on one of these, the hydrogens basically are flat in the plane of the molecule. And the other one, they are going up and down. If you actually make this molecule, this is true. One of those carbon's hydrogens are perpendicular to the other carbon's hydrogens. If you were to look at it edge on, carbon to carbon to carbon, there's some hydrogens on the far one going this way and some hydrogens on this one going this way. So basically this is an eyeball looking this way. They are perpendicular to one another. This is what we actually see. These p orbitals that aren't used in hybrids are what makes our double and triple bonds. Let's look at a few other ones real quick. CH4 was tetrahedral. It has 4 things around it. And so we would say, well, if you got 4 things and you got to spread out tetrahedrally, well, that takes 4 orbitals to do. So 4 things around my center is an sp3 carbon. My carbon is sp3 hybridized. If I have NH3, that was a nitrogen with a lone pair, hydrogens, hydrogen, hydrogen. That's still 4 things. Lone pairs occupy hybrid orbitals. To balance all the other things around our atom, we still need to balance the orbitals. Those lone pairs take up a hybrid orbital. And so this is still sp3 hybridized. The nitrogen is an sp3. It is only multiple bonds that are going to cause our hybridization to undo. And so if I have water, oxygen, lone pair, hydrogen, hydrogen, that is 4 things. That oxygen is sp3 hybridized. But when we think about that oxygen on carbon dioxide, well, that oxygen only has 3 things. A carbon and 2 lone pairs. It is sp2 hybridized for that oxygen? It must be because we need an open p orbital to form that double bond. And so much like looking at the number of things for VSEPR theory to find the shape, we can look at the number of things to find the hybridization. How many hybrid orbitals was needed to create that shape?